Well, welcome to today's Oracle Machine Learning Office Hours Usage Highlight session, leveraging OML algorithms in retail science platform fraud detection. So we're happy to welcome our guest speakers, Su-Ming Wu, a Senior Principal Data Scientist, and Sajith Vijayan, Senior Director of Data Science for Retail. I'm your host, Mark Hornick, with Oracle Machine Learning Product Management. So in today's session, Sajith and Su-Ming present how the retail science platform, and specifically Oracle's point of sale solution, Oracle Retail XBRi Loss Prevention, leverage OML's in-database algorithms. We'll see how they help avoid fraud by cashiers, as well as fraud tied to customer accounts. The solution flags outlier cashier behavior and customer behavior, delivering information to the retailer for further investigation. And next week, our data scientist, Ji Lu, will share best practices for using machine learning regression metrics. Regression supports predicting a quantity, that is some numeric value. Standard metrics for evaluation include mean square error, root mean squared error, the mean absolute error, and R squared. Well, what's the difference? Which should be used? And how does the metric translate back to the business world? How do we compute regression metrics in a scalable way using OML for Pi? And G will address these questions next week. To learn more about Oracle Machine Learning, check out our webpage on O.com and explore OML using the Oracle Live Labs, where you can quickly spin up an autonomous database and work through various use cases with OML technology. Visit our site with this QR code and try the OML for Pi Live Lab just highlighted at Oracle Database World. Included with OML notebooks are template examples for our SQL and Python interfaces. We've recently expanded the set of notebooks to include all the algorithms supported by OML for SQL and OML for Pi, along with other features. Also, check out the examples at our Machine Learning GitHub repository, which includes a broader range of notebooks and scripts for use with OML components. And of course, through our OML office hours, see the rich library of recorded sessions that highlight product demonstrations, use cases, and application integrations. So now we'll switch to Sajith and Su-Ming for leveraging OML algorithms in retail science platform fraud detection.
Thank you, Mark. So as Mark mentioned, we are part of the retail global business units. Our mission is to solve data science problems using Oracle OML and an Oracle database. So our products try to solve three kinds of problems. We have our platform has prescriptive, predictive, and predictive and prescriptive problems we try to solve. The platform is run on an Oracle database with ADW instance and uses OML for its solutions. You can see from our retail science suite, it solves various retail business problems, which includes affinity analysis, store clustering, customer segment, customer decision, demand transference. The beauty of this is that, as we say, don't move the data and have the data in the database and use OML for SQL to solve the business problems. So in today's session, we're going to focus on one retail problem, which is called fraud detection. And the following sections will continue to expand and tell you how we productize our solutions using OML. The reason we are able to use and go to market with a platform with various retail solutions is because we have a database which has 2,000-3,000 tables, which covers all the functional features of various retail data. On top of it, we have various metrics we already pre-calculated and then feed it into the OML libraries. So it makes it very easy for customers to turn on various solutions and use data science to solve their business problems. So in this model, I mean, this is just a simple view of all the various functional areas or functional tables we have in our database schema. So it pretty much covers any problems you want to solve in retail. With that, we have also an extension framework called Innovation Workbench, which allows customers to build their own data science models on top of it. And this just screens that once the data is there and the analytics are done, there should be an easy way for visualization for the customers to see the results, right? End of the day, any data science problems, we need the customers to be able to see. So we have various tools, front ends, we build out of the box, and we use OAS and DV to show the results. Today's focus, as I mentioned, our platform solves a lot of retail problems, which includes assortment optimization, forecasting, market basket analysis. But today's focus is going to be mainly on fraud detection. And why, even from this slide, you can see the investment on fraud detection problems across retail has been low. And that's why I think it is basically because no one's using the data science solutions and people are trying to use rules-based solutions, which can be costly to maintain. You can see the industry is almost 123.4 billion. There's a lot retail shrinkage, average retail shrinkage. And then you can see 39% of it is from dishonest employees and 38% is shoplifting and 16% of them. So I think from this section, you can see how we can solve fraud detection and how we can use data science to do that.
Thanks, Sajith. So let's first talk about what the traditional approach is. So Sajith sort of mentioned it already. So what retailers usually do is they use sort of rule-based filters in software to flag the suspicious cases in the database. And then after that, what happens is expert investigators at the retailer examine these cases to determine whether fraud has actually occurred. So there's no way of avoiding human involvement here because you never, for various legal and ethical reasons, you never really want to automatically determine fraud. That's not a good idea. But what the software does is it winnows down all these vast number of cases down to something that's manageable and that the human experts can look at. So that's what we're going to talk about today. What, instead of doing rules-based software, is there something else we can do that might be better? So what are the limitations of doing rule-based? Well, the typical problem is actually they can flag too much. You've got too many cases to investigate, and you also have no indication of which to investigate first. So then sometimes retailers just say, well, I'm just going to give up. I'm not going to do this, right? The other problem is it might miss, rules might miss new types of suspicious activity because they might be very different from what the rules were coded to look for. And by the same token, the rules may require manual change when the business changes or when new fraud behavior is discovered. So we'd like to avoid this if we can. So what's the possible remedy? So we can think of the fraudulent cases as being outliers. Okay. So if we had some sort of machine learning method that could just learn what normal behavior was, okay, then if it learned normal behavior, it could flag outlier behavior. And if normal changed over time, then through retraining, it could learn what the new normal was. So this sounds good. It solves some of the problems of rules. It's also a good approach if the normal behavior is actually the vast majority of instances, which is true in retail. Okay, so fraud is an unusual case. So fortunately, so how do we do this? Okay, so you are probably familiar with support vector machines as classifiers, right? So as binary classifiers. So if we had labeled instances of fraud, not fraud, what we could do is just use, for example, the support vector machine in its traditional role as a binary classifier, fraud, not fraud. And what it tries to do is draw a border, right? Draw a boundary between the fraud and not fraud cases. And then that's you apply this border to determine for test cases whether it was fraud or not fraud. So we're not going to do that here. Okay, that's the traditional way of using the support vector machine. We have a different approach here. So this is actually it's the same support vector machine, but you use it in a mode called one class mode. Okay, and this is supported by OML. In fact, the suggestion to do this comes from the OML team. So in the one class case, what the SVM does, it does still draw a border, but it tries to draw a border around all the instances. All right, so that's what we have illustrated here. These little triangles are customer accounts. Okay, I'll explain all that later. But they think of these black triangles as individual customers that have visited the retailer and have made a purchase or some sort of transaction there. All right, so we call those customer accounts. And these are there for this illustration. We only have two features. All right, we actually have many more. but I will get into all that later. Okay, for now, just imagine we only measure the customer accounts on 2 features, and we run the support vector machine in one class mode. What is it going to do? It's going to try to draw a boundary around the vast majority of cases. And then what we will know after it's done that is cases, okay, customer accounts that are very near the border or even over the border, okay, will now be the unusual cases, and we will flag those. And the one class support vector machine will do that. And that will be the basis of our fraud detection. We will tell the human investigators, oh, you should investigate this one and this one, for example. So that's the idea. So now we're going to go into all the details of, making that work in the retail setting. So the important point here is that the one class SVM is an unsupervised method, right? Because normally we use SVM, as I said, in a supervised mode where we are, as a binary classifier, we're not doing that here. So we don't need labeled instances of fraud and not fraud. So why is this an advantage here? So although almost all retailers do fraud detection, so many don't actually have, they don't actually keep good records of past fraud behavior. The other problem is fraudulent behavior is quite rare. So even if you had those records, positive instances would be quite few among all customer transactions. So from that alone, supervised approaches may be questionable. The other problem with fraud, the other problem here is the fraud investigation is quite labor intensive. You remember I said you have to involve human experts in that. So since it is labor intensive, that's going to further decrease the number of positive instances, right? Because the retailer, maybe they don't have enough experts to examine everything, for example. Okay, there's actually 2 kinds of ways when we're talking about retail that fraud can happen. You can say that the customers of the retailer commit fraud. It can also be that the cashiers commit fraud. And then there's actually a third one where cashiers collude with customers. We lump that in with the customers, okay? So we're gonna mainly in this presentation consider customer fraud here. And I will make a few comments about the cashier case, but we don't have time to cover both of those in detail. So we'll just do the customers. So we don't actually look for fraud at the individual customer transaction level. We don't go transaction by transaction and try to say, this is an outlier and this one isn't. What we do is we actually look at the aggregate behavior of a customer over time, okay? So the first thing we do, we actually aggregate the transactions. So we don't necessarily know the customers individually. What we have is probably a customer, what we call a customer ID. So that may be, for example, a loyalty card ID for the customer, but it can also be a credit card number. Okay, so you don't necessarily have a one-to-one mapping there. It could be that you have 2 credit cards for a given customer. So we don't worry about that. Okay, we do just, so think of this customer ID as being an individual, as a unique credit card number that we identify a customer account by, right? So given that, what we do is we still aggregate. So for example, these 2 transactions, all right, they got aggregated into a single summation, okay, for customer 2234 and so on. Same thing for all the other customers. So in the end, we have one aggregate for each customer ID, all right? So that is our input data, okay? So the input data is these aggregates, these customer aggregates, not the individual customer transactions. So what that means is actually we are looking for, so we're looking for suspicious behavior over time, right? We're not looking at individual transactions. We're seeing over time, is this customer suspicious? We talked about the customer aggregates. There's several steps we go through. Of course, feature construction, and then we do something called rules-based filtering. And then after that, we actually use partition models. And I'll talk about all these in detail. That's actually the rest of the presentation. So yes, we use create model, of course, but we use it in the partition model mode. I will discuss that as well. So let's talk about the features that we use. And this is features, keep in mind, I'll discuss mostly features for customer accounts. As I said, we're going to focus mainly on that. So when you construct the features, domain expertise is certainly crucial. You should use features that human fraud investigators have used in the past. And in fact, one of our team members actually had done numerous investigations. So that was actually essential to getting this project done. So what kinds of features do we use? So one principle that we used is to prefer ratios rather than absolute quantities. Here's a little very small example. So one way that fraud occurs is actually by returns. Okay, so I'll just give you that little tidbit of information. So, for example, if a customer returns a lot of stuff, does a lot of return transactions, or has a high return dollar amount, that may be an indication of fraud. But you actually want to use ratios to detect this, right? So here's two small examples. So this customer has a higher total return dollar amount. So this is at this moment in time, at this snapshot in time, this customer has returned $200 worth of stuff, say, okay? Whereas this customer, the 2267, has only returned $160 worth of stuff. But the only reason customer 2139 stands out a little bit more is simply because this customer has shopped more frequently, has the total number of transactions. And so that's sort of led to a total higher number of return transactions. But what we really want to do is take a ratio. We want to see the dollar amount per return transaction. So then it's a little bit different. It turns out that this first customer, 2267, is probably the one that we should pay attention to first rather than this one. So that's a very simple example of why you would want to use ratios rather than absolute dollar amounts when we're looking for outliers. So you don't want the SVM to take these as being the indications of outliers, but rather the ratios. We use a lot of several different kinds of ratios. We have ratios of columns that both contain counts, integer counts. We have ratios of dollar amounts, and then we have averages, right? So that's just an amount or a count, actually, I should say, divided by some other count. And the two columns, of course, should be related. I'll give some more examples a little bit later. Here it is. So we talked about returns being a way of committing fraud. So we actually have two different ratios here. We have the percentage of total transactions by the customer. That's what this denominator is. Total transactions by the customer. And remember, I said we're doing aggregates, right? So this is an aggregate count this is a snapshot, an aggregate count of all the transactions the customer has done and what fraction of those involve returns. Same thing here. This is, we already saw this. In fact, this is the dollar amount per return transaction. So the other way of committing fraud is through voids. Okay, that means that the customer, the cashier, entered the purchase into the point of sale device. Okay, but then voided that transaction. So it turns out that's another way fraud can happen. So we have similar kinds of ratios for looking at fraud, right? So these are all ratios, and we feed these. This is an example of what we feed into the anomaly detector, the one class SVM. So we were talking about features for the cashier case, and as I said, the customer case. As I said, there's another way that fraud can happen, which is through cashiers. So I'm not going to go into all the different features we use for cashiers. Just want to point out the contrast. There's actually an interesting, from a data science point of view, there's quite a contrast between the two types of data. So that's actually why that's one reason we need separate models, in fact, for cashiers versus customers. I mean, first of all, the features are different. And second of all, the nature of the data itself is very different. So for example, the data instances, right? You have millions of customers, but cashiers, that's more or less a fixed pool, right? I mean, yes, they can quit and you can get in new cashiers, but more or less that's a fixed small pool, relatively small compared to the number of customers. The other thing is that there's a big difference in the feature counts. So you actually have a lot more features with cashiers because their behavior is very closely monitored by the point of sale device. And I think even these days, there's even video surveillance of cashiers. So there's actually quite a few features you can construct here. And also the other obvious difference is the transactions, right? So customers, maybe it's 10 transactions per customer or whatever. Anyways, in the tens, whereas obviously for cashiers, they're handling thousands probably at any given snapshot, right? So that's an indication that we certainly need different models and that the two cases are rather different. Okay, so training the models. So again, we're going to focus just on the customer case. So here's an interesting recommendation we had from the OML team. So you should actually, if you have an existing rules-based system, which frequently you do in fraud detection, because usually, as I said, the traditional way is to actually use rules. So you probably have those. So what you want to do is use those rules to exclude cases that the rules are going to exclude anyway. And why do you want to do that? So from the OML team, we understood that you don't want the SVM to consider the anomalous cases as normal. So you want to do your best to try to get a set that you're sure is normal, represents normal behavior. And if you have rules, well, why not use them? So that's in fact what we did. Okay, so that's actually what that was on the flow chart I showed earlier. And that's why we do it. So the other thing I mentioned earlier is using OML's partition models. So here's the details of what we do. We take the customer day aggregates. So I'll discuss the 90-day annotation later. So this is the customer aggregates that we have been talking about. So we partition the customers by their total transaction count. So these are aggregates. We have as you saw earlier for the features, we have a total transaction count of that snapshot in time for the set of customers. So from there, we create partitions according to ranges of transaction count. So in our product, the ranges are actually settable by retailer. Okay, so it's configurable by retailer. I've just chosen some simple example here, 0 to 5, 6 to 20 transactions, and then greater than 20. So these are our 3 buckets. What we wrote software to do was then assign a partition ID to each of the configured ranges. Okay, so I've just chosen partition ID 1, 2, 3. We feed those into the create model. In a partition, we use OML create model for partition models. And then what we get out, what OML produces is we actually, in this example, we would have 3 different one-class SVMs to handle each of the ranges. Okay, so the reason we do that is our expert advised us that normal behavior is frequently different for these ranges. So that's why we have the ability to configure ranges, both the number and the range intervals. Okay, so how do we actually, so what's an example of how we actually call the create model? So we use settings table, which you're probably all familiar with. We set the partition ID. So that's exactly this partition ID column. So that's our column to partition on. This WID, it's a customer account ID column. And this table here, this is the result. Okay, this is the result of doing the aggregation and also the result of doing the rules-based filtering, and also has the partition ID in it. So it's all 3 things, right? Aggregation, rules-based filtering, and partitioning. So this is unusual. The target column name, usually this is the binary classification if you're using SVM in the normal mode. Here you can put null, that indicates that you want to create this one-class SVM. And then this table model settings, I just made up a name for this table here. So we also refresh the models, right? So it's important not to have the models become stale. It's possible normal customer behavior may change over time. We actually used a very simple approach here. Because we're not training all that many models, what we do is we simply just retrain on a regular basis. Okay, that's actually our approach to refreshing, and it works for us because we don't have that many models, so it doesn't take that long. So we actually use a rolling horizon of 90 days, well, yeah, 3 months as shown in this diagram is really 90 days. So at the end of, say, March, what we do is we train on all the on March and then the previous 2 months. Okay, and then again, we retrain a month from there. End of April, we retrain again. Okay, except that it's a rolling horizon. So we again take only the last 3 months and again at the end of May. You could actually set the training interval to be, the frequency of training to be more frequent than what I've shown here. That's also settable in our software. I've only illustrated the sort of monthly training case because it was easier to illustrate that. So, but the main point here is there's a rolling horizon where we keep refreshing the models using the latest data. Okay, so we've covered the training. Okay, so now of course after we train, we actually want to do something with these models. We want to predict with them. So the data flow is not the same. It's not the same as what we just discussed for training. So actually the first 2 boxes, these are the same. We do the customer aggregates, we form the customer aggregates, we do the feature construction. Okay, but we don't want to do the rules-based filtering, right? You don't want to, the whole point is you want to keep those anomalies, you don't want to get rid of them. So in the training, there was a box here for rules-based filtering. We don't do that. You do have to do the partitioning. So we do the partitioning, we assign, partition ID to correspond with the partition ID we use during training. And then we send all that into prediction. The other aspect is, of course, we predict more frequently than training, or we could, all right? We might want to predict daily, okay, in our case. So we run this daily, we give the retailer a new set of anomalies every single day, right? So that's run more frequently than training. That means all these steps are run more frequently. So these customer areas and feature construction, these might be run daily, and then it's okay because the training required required these less frequently. It's okay, so it's okay if we just construct these daily. That's fine. So how do you get the anomaly score from OML? So there's a prediction probability function. You give it the model name. Okay, I just made up a model name here actually. The using star means to use all the columns. Okay, and this customer features table. So this is the result coming out from here. All right, so we take all these steps. This goes into that table, customer features, and we run the prediction probability function. That gives a number between 0 and 1, and 1 means higher anomaly. So, and as I said, we run this more frequently in the create model. What that therefore means is customer features, it will contain data not used during the last monthly training. Let's say we're training monthly, right? So that could mean, for example, that you have new customer IDs, new customer accounts in this table that were not in training, for example, right? So that should be fine. So once you've run all that, you want to display this information to the user. So our suggestion is you actually display both the new anomaly score that you've gotten, and you also display your old rules-based results. Okay, because why? Because users are used to the rules, right? They've been using them for a while, so we don't want to get rid of them entirely. Besides, we're using the rules for filtering anyway, so why not show all this? So what we have is the customer accounts, we have the anomaly score, and it's also helpful to be able to sort and filter by anomaly score. So this is nice because now the fraud detection experts can say, okay, well, now I have an order in which I should examine these customers. So I'm going to examine this customer first. Okay, so that's something that you might not get with the rules. You may not have, your rules may not give you a sort of ordering or the ordering may be much cruder. Okay, so you don't know which one to investigate first. Okay, so that's actually the content of what I was going to present. I'll just summarize when should you do all this? When is fraud? When is anomaly detection a good idea? So you have, as we said, labeled data, right? You want to do a binary classification, but these things might prevent you from doing that. Your labeled data is either unavailable or it's spotty or untrustworthy. You have very, very sparse availability of positive, that is to say fraudulent instances. So normal behavior should be the vast majority of instances, so you should be sure about this one. And so the last one is not a must-have. You can do all this without having rules. All you have to do is skip that part about filtering by rules. But if you do have them, then you should use them to eliminate, during training, you should eliminate the likely fraudulent cases. Principles of feature construction, as we said, you need experts to help you with this. This does require domain expertise. Use ratios, that's likely to work better than absolute quantities. So building the models, so filter by the rules. If you have the rules, use some kind of refresh strategy. We've picked a particular one, a rolling 90-day horizon. Oh, by the way, the 90, of course, is configurable in our system, but yes, in this example, it was 90. And use OML partition models. That feature is very handy if different ranges of data have different normal behavior. Again, that requires domain expertise to assess. So for prediction probability is actually what we use. It's actually only one option. There's also the OML apply function that will do the same thing. Of course, do not apply your rules-based filters here. You don't want to eliminate anomalies. And present the information in a way that allows sorting and filtering by anomaly score. So one key point is that the prediction probability will allow the expert to know which one to examine first.
Well, thank you very much, Su-Ming and Sajith, for that great presentation. If there are any questions, you can please add them to the Q&A and we'll address them here. So in case of using the OML partitioned models, how much time do you estimate that saved you as compared to if you had to do that manually, that entire process manually?
Oh yeah, right. That's a good question. Yeah, so that saved quite a bit of coding time because I mean, you could code. We could have coded, partitioning manually. But yes, that saved a fair amount of time. Actually, I maybe an estimate. Maybe like a couple of weeks of development time there. Actually, I mean, yes, we could have coded all that, but yeah, we didn't have to. That's right.
And in terms of sort of the user response, I mean, oftentimes users want to understand, why something is being flagged. What have you found with that?
Yeah, that's so the presentation was already getting quite long, so I wanted to include this, but now I have a chance to talk about it. So there is a prediction _ details function, which I did not mention here. So it's a companion to prediction probability, prediction _ details. What it does is it tells you which features. It actually gives you a ranking and a weight. Okay, I guess it gives you a weight. So it gives you a weight for each feature of how much that feature contributed to the number given by prediction probability. So this is actually great, and we use it. Okay, I didn't go into it, and we use it. So actually, in this UI, we actually don't just have the anomaly score. We actually also show the weights. The weights given by prediction details. We actually show all that. Okay, so that the user can say, oh yeah, well this has a high anomaly. Why? Well, I'm going to look at those prediction details columns and now I'll know, oh, it's because, voids. This customer had a very high percentage of voids. So that's why, or it was a combination of voids and returns. So that's actually very helpful because now the expert, when they go to investigate this particular customer account, they will know what to look for. right? So that's actually great, yeah.
We have two questions that just came in. One from Shankar. Can you generate some sort of rules in terms of features from the anomaly prediction results?
Oh, good question. That's kind of asking, I guess that's kind of asking is sort of the explainability question maybe. Well, okay, so you can use what I just said, I suppose. If you could try to use, if you notice a pattern over time with the results of prediction details, right? If you happen to notice that, for example, returns seem to be playing a very big role in the anomaly score, then you might, that's a good suggestion as to maybe developing a rule that's specifically for returns, right? If you didn't have one before, for example. So yes, you could use the prediction details you may be able to use the prediction details to develop new rules that way. Yeah.
And another question from G, how to deal with the case that the two methods have different results? There's a part two. So how about cases where that are not detected by either the SVM model or the rules-based system?
Yeah, that's a very good question. To be honest, we don't quite have enough experience, okay, with a variety of retailers to quite answer that question. What we really want to do over time is look at the correspondence, between these two columns. We don't quite have that. What we're doing right now is suggesting to retailers that they mainly use this as a way to figure out what to investigate first. Okay, so as I said before, we're not recommending the abandonment of the rules because users have been using rules for a very long time. We don't want to just say, just get rid of it. No, we don't want to do that. So yeah, right now we're mainly using it as a way for indicating to the experts what to investigate first. So yeah, I don't have a good answer. It's just the upshot. We need more experience with the system, actually.
Sure, fair enough. Saeed asked the question, how did you choose the threshold for the anomaly score to classify as fraud and non-fraud?
Yeah, good question. So we don't have a threshold, in fact. We just simply, what we do, let me see if I can go back to, we simply run this over all the customer accounts that there are, right? So customer features, remember how we do that? We take all the customers, all the customer data, create features from them. So we don't exclude anything. And what this means is we're actually generating prediction probability for everybody, okay? Everybody gets a prediction probability. We don't have a cutoff here. The user can use a cutoff. Again, we don't quite have enough experience to say what a cutoff might be. So we fall back on what I just alluded to. We sort by the anomaly score, and they can invest. This gives the retailer an order in which to investigate these, and because they are usually time constrained anyway. Okay, as I mentioned earlier, fraud investigation is quite labor intensive. So you're not really going to investigate everybody that might look fraudulent. You just have no time to do that. So the best we can do is give them an indication of which to investigate first, right? Which are the ones that stick out most. We don't have a cutoff, not yet anyway. They do a sort.
And Saeed mentioned then, therefore, how do you choose which cases to investigate further or not?
Yeah, that's simply by sorting. Actually, that's what we're recommending right now. It's simply you investigate the ones that are most outlier. Okay, you go in order of most outlier down to least outlier, and that's where we think our system has an advantage for them.
Shabir is asking, do you use ROC curve to differentiate the threshold for fraud and non-fraud?
No, we don't. We're quite primitive at this point. What you've seen in this presentation, that's our entire system, actually. Yeah.
So I thank our speakers very much for their presentation and Q&A, and we'll look forward to seeing you next week for our next session. Thank you, everyone.